Hi, my name is Luke Wisner, and this is my reinforcement learning algorithm that improves on Dijkstra's algorithm to solve a user-generated maze. It uses the DE1 SoC, a speaker, a keypad, and it utilizes the VGA port to display graphics on a monitor. So I have an example maze up here that I will use to demonstrate how both algorithms function. So how Dijkstra's functions is it needs to determine if certain spaces are nodes or paths. And how that works is it'll start at a point and it'll check every point around it. And it'll check which of those are valid. And from there, it'll assign, oh, does it have one possible move? Or if it was up here, it would have 3 possible moves. Or if it was just in a space like this, it would have 2 possible moves. So anyone that has more than 2 possible moves is a node. And that's an important space because what it can do is it allows us to move in different directions instead of just moving along one concrete path. And nodes are important, which is why we save them in the code. So how that works is it'll move along here, and then when it gets to a place that has more than one valid move, it'll then choose between these two, and it'll take a valid move. Now, if it continues to move along here, using just the path function, it'll come to this point, which is a dead end, because it only has one valid move. And what that'll cause it to do is it'll retreat back to the previous node. And now that we're at the previous node, we store this previous node move. So we know that from this node, if we get up to the top and have to come back, that this is no longer valid. So we then close this off, making it so we can never go back. The algorithm then runs up here and eventually gets to the end, and then it exits the while loop, and it explains how many tries it had. Now, I'm using tries to quantify which algorithm is better, because what it does is it explains how many times do you have to hit these walls to determine when you're there. How many different failures do you have to get? And that's what I set out to improve on with my algorithm. What my algorithm does is it takes one point, but it makes a random move. So it moves in a random direction instead of checking everything around it for valid moves beforehand. So it'll move in a random direction, and then if it hits a wall with its random move, it then takes the X and Y coordinates for this wall and stores it so that it never hits it again. So that way, if it's going to move here, it'll know, oh, this is a wall. I already know that, and I know that that's bad, and it'll continue to move. And so it has a similar function here where if it hits a dead end, it'll go back to the previous ones, basically filling these in with walls as it goes so it knows to never return to those points. But the difference with mine is that it doesn't check everything every time because that's very redundant. Dijkstra's algorithm will be checking many things that it's already checked before, while mine moves randomly and knows, it remembers what it's checked. So it remembers which places it can't go to, and it'll eventually get there, and then it'll return how many tries it took. Now, to demonstrate how the maze building functions and how the algorithms work in real time, I'm going to just enter the make file in there, which will start us with a new maze, and then we use the keypad down here. So what I did is 2 is up, 4 is left, 6 is right, 8 is down, and then 5 is select or deselect, and then the pound sign here is what you use to enter the maze. There's also a speaker, so when the first algorithm runs, it'll play a little tone, which you'll hear later, and then when Dijkstra's algorithm runs, it'll play another tone as well. So if you hear the 2 tones, you know that both are running, and if you only hear 1 tone though, that means that only mine has processed and that the maze is unable to run. So now what I'm going to do is I'm going to use the keypad to show. If I hit 6, we move over like that, and it updates. It's the same with hitting 8 to go down, or 2 to go up, 4 to go left, and we can essentially move this cursor around like that. Now if we hit 5 on one of these spaces, what it'll do is it'll then fill it. So we can use this to move the cursor around, filling spaces as we go, or unfilling them. So what we can do is if we go back over to this space, and we hit 5 again, we can now see that it's cleared. So if you make a mistake, you can always go back and fix it. So now we can just draw out a little maze here. We'll just do a simple function. where what we'll do is we'll just make one path and show how that functions, and then we'll close it off and we'll show how the dead end checker works. So let's say we just make one path in here. Now we can hit this button to start the program at any time, but to show, mine is going to move randomly through here, occasionally bumping into walls, but then never bumping into them again. What Dijkstra's is going to do each time is check every single spot, which means it's hitting more walls constantly and taking more tries as it goes through here. So we can see there's 6 points until we hit the end. So Dijkstra's is going to end up taking 12 tries if we count all of these, because it's hitting 2 of these walls every time it moves up. So now what we're going to do is we're going to submit it. You'll hear the tones, and then you'll see here how many tries are displayed. Okay, perfect. So now my algorithm is done. Dijkstra's ran. So mine took 6 tries to solve the maze, and Dijkstra's took 12, just like we guessed. So that shows that mine is more efficient for something like this. So I once again built the same configuration, but what we're going to do this time is we're going to block this space right here off. So now it's impossible to get to this end goal. So what's going to happen is mine's going to run through here, it's going to detect this place, and it's going to realize that there aren't any valid moves, so it'll fill it, and then it'll retreat back to here. And then it'll realize that now that this one is a wall that can't be moved into, that there are no more valid moves, and it'll retreat and basically fill in all of these spaces until we get to the end. And once we're at the end and we have no more valid places to go, we know that it doesn't work. So now I will submit the maze here, and this time only mine will run, because it'll determine that it can't be solved and Dijkstra's won't run at all, which is why we'll only hear one tone this time. And sure enough, the maze could not be solved. Please make a new maze. So now I've created another example maze just to demonstrate that the code can also function with more than just one dead end. So now we have 2 dead ends, but it will still be able to run because each algorithm has a way of encountering a dead end and then retreating back and closing it off so it doesn't hit it again, which it can do with multiple, which we will see right here if we submit it. We have our 2 tones, and then as we can see, it took my algorithm 6 tries to solve the maze, and it took Dijkstra's algorithm 20 tries to solve the maze. So we can see that this one took it a little bit longer, but mine is still more efficient. So this project certainly wasn't without its challenges. Some of the main issues I faced were how to implement this dead end function at all. So some of the problems I was running into was I would hit it, but then the program would get stuck. And that was an issue because it just wouldn't move further, it couldn't find a valid place to move, and it would just sort of stop. So I had to implement the dead end functions into both that had the different ways of allowing them to retreat back to a previous valid state and then fill this in so that it wouldn't go back to that point and get stuck all over again. So that was definitely a challenge that I faced. Another challenge that I faced, which was a little more minor, was that I was reading these in my 2D array as going across the rows being X's, columns being Y's, like normal. So I was putting it in where it was the array and then bracket the X coordinate, bracket the Y coordinate. That, however, wasn't true. What I actually needed to do was the first bracket goes to the Y coordinate, and then the second bracket goes to the X coordinate for our 2D arrays. That was a little hiccup that it took me some time to figure out, but I eventually got it. Another issue that I was facing was, how do I store each of these wall values in my algorithm? And I thought back to our first Lab 1 when we learned about pointer vectors, and I ended up deciding that that would be the perfect time to use linked list. So what I did was I created a pointer vector that would store an array of these values. So when it hit a point, it would then take those values and it would grow the current failure vector that we already had, and it would then add those two to it. So that way, every time we're going to move, we then run through and check that entire vector and see, oh, do our x and y match any of the x and y's inside of that vector? And if they do, then we know that we just shouldn't go there. And that also corresponds to the check previous function that I wrote as well. So we have our check failure, where it won't move if it knows it's a failure, and our check previous, where it won't just move backwards. Because a lot of the times, it could get stuck, where it would be in a place where it could move, and it would just go back, it would go forward, and it would go back. So essentially, I used that to also determine if there was a dead end. So instead of it checking if there was one valid place to go, it would check if there were 0 valid places to go. So that way, moving backward wasn't a valid choice, and it would know, okay, this is a bad spot. And that is my maze function. I'm very happy with how it turned out. There were certainly some challenges involved, especially with detecting the dead ends and being able to retreat back to a previous state and then closing it off so it never goes back again. But I've proven that my algorithm is more efficient ultimately when it comes to navigating a maze like this.